We'll have the equation as Q reversible. In the differential form, we have Q reversible, work reversible. dH basically represents du plus pdv, which is the internal energy plus flow work. This is a combination property, kinetic change and potential energy change. And this equation is in the differential form. The state functions are in exact differentials, and the path functions are represented by inexact differentials. Now, you know that del Q reversible is essentially equivalent to TdS, and the second of the Gibbs equation, it says that TdS is essentially equal to dH minus VdP. So we'll plug in this TdS instead of del Q reversible, and we'll have an equation in which dH minus VdP and rest of the equation remains the same. dH would essentially cancel out, and you'll have work reversible equivalent to minus VdP minus change in kinetic energy minus differential change in energy in potential energy. And when you need to find out steady flow work, you'll have to integrate this between the two states, 1 to 2 integral VdP. VdP basically defines the path. The kinetic energy change and the potential energy change. And when you have negligible kinetic and potential energy, you would essentially have kinetic energy and potential energy ignored, and work reversible would be equivalent to minus VdP integral 1 to 2. This is for steady flow work, that is the devices that operate under steady state conditions in an open system. When you have incompressible process or incompressible fluid, such as liquids, you will have V out of the integral, and the integral of dP from 1 to 2 would essentially be P2 minus P1. This is the reversible work for a incompressible fluid. Now, in a case where you have diffuse nozzles and pipes, work is essentially zero. You don't have any work involvement in there. And since work would, your essential equation would be Vp2 minus P1 square 2 minus V square 1 over 2, which is change in kinetic energy and change in potential energy. This is the famous Bernoulli equation that you must have encountered in your fluid mechanics course. Now, to summarize, the reversible flow work in flow systems that are the open systems, work reversible is integral 1 to 2 VdP. This is the reversible work. And in closed systems, the work reversible is defined by the boundary work, which is PdV. So it's exactly the opposite of what you see in closed systems. Let us have an overview of an example which says you have to determine the compressor, or you would say a compressor slab. To compress, it could be steam or saturated liquid. In case of pumps, it is saturated compressor at least equal to 100 megapascal. So you have temperature entropy diagram, as you have for temperature specific volume. The trend is generally the same. The constant pressure G.
So slide changing, it's a previous slide.
Are the slides changing now or not?
Okay.
No, sir.
Let me do it again. They're not visible to anyone?
Yes, I have visible.
Yes.
All right. So you have an example where you have to find out the or pump work, both compressor or pump work input required to compress steam or saturated liquid. For pumps, you'll have saturated liquid. For compressor, you'll have steam from 100 kilopascal to 1 megapascal. So essentially, you are having a plot on temperature entropy diagram at the moment. It is the same thing as you have a plot on temperature specific volume plot. The pressure lines are having the same trend. These are the two pressure lines, the 1 megapascal line and the 100 kilopascal line. So these are the two lines. This first line is 1 megapascal line. The second line is essentially 100 kilopascal line. So you have two conditions. The steam, which is acting as saturated steam, is compressed, or saturated vapor is compressed from 1 to 2 isentropically, so that your entropy change is zero. And in pump, you have to compress saturated liquid from state 1 to state 2. So this is where you have the first part for pump. This is the second part where you'll have for compressor. Both are compressed isentropically, and you have to determine the compressor work. Compressor work in this case would be simply, in both the cases, would be simply the change in enthalpy, or we'll look it into in this way, that if we consider the first part, this is where you have liquid, this is where you have steam. In case of liquids, the relationship is same. You have to find integral 1 to 2 VdP. But in the case of liquids, since you say that dV is approximately equal to 0, you can say that V is constant, and V you can find out for state 1 as Vf at 100 kilopascal. So this is for saturated liquid. You'll have to multiply it by change in pressure. Change in pressure is 100 kilopascal, 1000 kilopascal, which is 1 megapascal, and 100 kilopascal, which is this pressure for state 2. You just have to apply the formula and you'll get the reversible work in for the case of pump, where you have fluent as the saturated liquid. The second case is you have to find for the steam. Now for the steam, you know that V is not constant, and you have to integrate from 1 to 2 VdP. So either you have a relationship between specific volume or pressure, or in other words, the second Gibbs equation says that TdS is equals to dH minus VdP. Now since it's an isentropic process, ds would be essentially 0. So this whole term would be 0, and dH would essentially be equal to VdP. So you can replace VdP with dH, and integral of dH would essentially be the difference of the enthalpies, H2 minus H1. And now if you consider the enthalpies at the two states, at the first state you have 100 kilopascal pressure, saturated vapor. You will directly read the value from the table. Also note down the entropy value, since the entropy at state 1 is equivalent to the entropy at state 2. So what you can do is that you can go to the pressure of 1 megapascal and take the entropy at the first state equivalent to that at the second state, and find out the enthalpy value at the second state. You just have to take the difference of the two, and that would give you the compressor work for the steam. Is it clear? Moving on to the property diagrams involving entropy and isentropic efficiencies of steady flow devices. So normally the diagrams, temperature entropy diagram you have seen, enthalpy entropy diagrams are normally used for adiabatic steady flow devices. So steady flow devices such as turbines, compressors, pumps, fans, nozzles, diffusers, these diagrams are very essential in those cases. If you have a steady flow device having an adiabatic process, then on an enthalpy entropy diagram, the vertical distance delta H on an enthalpy entropy diagram is measure of work. So the difference between H1 and H2 would give you the work that is either being provided by your device, or it is consumed by your device, depending upon which way you are going. If you are coming from 1 to 2, the work is produced in the case of turbine. If you're going from 2 to 1, it is the opposite. But in both the cases, the horizontal distance delta S increases, and this is the measure of irreversibilities. As your system moves from 1 to 2, your delta S would increase, and this is the measure of irreversibility. This specific plot is common with turbines. If you'll have compressors, the plot would look something like this. your enthalpy change would be there, still there, but entropy would increase. Compressor work won't have a negative entropy, so it would have a positive entropy. Your entropy would essentially increase. This would be your first state, this would be your second state in case of compressors. We'll come to know of it. So the isentropic process involves no irreversibilities. If I have to make this actual process as an isentropic process, I'll have to have a vertical line so that the entropy does not change. And this serves as the ideal process for adiabatic devices, whether it's turbine, compressor, nozzle, diffuser, ducts, wherever you'll have these kind of flows. So for an actual process, pressure and temperature are different at state 1 and it is different at state 2. For the ideal reversible process, pressure and temperature at initial state and the pressure at the final state, but entropy would remain constant at the two states. So this you should remember whenever you're talking about an ideal process or an isentropic process, your entropy would remain same. When you talk about turbines, the isentropic efficiency of turbines, let us have a look at the actual process and the ideal process on an enthalpy entropy diagram. So you have enthalpy entropy diagram. These two pressure lines, these are the same lines if you are in the superheated region. If you have this curve, this is pressure line P1, this is pressure line P2. So I have selected this region only for the moment since we are talking about superheated region. So this is the region which we are showing right now. If your system move, this is the inlet state. Let's say we are talking about a turbine. We are talking about a turbine. This is the inlet state. Fluid is coming at high pressure and high temperature. As the actual process takes place, this dotted process, your system moves to the second pressure, which is P2, which is the exit pressure. Now, if you see, as you move from 1 to 2, there is some work that has been generated. This is the work, actual work out of the turbine. Difference between the enthalpies of state 1 and state 2A. A represents actual state, actual process. If the process has been performed isentropically, inlet state would be the same, outlet state would be on the same pressure line, but it would have constant entropy. The entropy would not change. And you'll represent this process as 2S. This is the isentropic process or an ideal process. In this case, the work that you will get as a result of the difference between two enthalpies would be the maximum work that you can get out of a turbine for these two pressures. So when we have to compute the isentropic efficiency, the isentropic efficiencies is comparing the actual, the ideal work with the actual work. How? So actual work of the turbine is represented by WA, which is the difference between H1 and H2A. And the isentropic work, which is the maximum turbine work that you'll get, is WS, which is the difference between H1 and H2S state. So if you have a look over here, the isentropic efficiency of a turbine is essentially H1 minus H2A, which is actual work that you are getting out of turbine. And it is with regards to H1 minus H2S, which is the isentropic work that you get out of a turbine. Now, remember, whenever you have to calculate the isentropic efficiency, you need to have three enthalpies. One is the enthalpy of the inlet condition, which is the same for both numerator and the denominator. And the other two enthalpies are one for the actual state, other for the isentropic state. So you need to have three enthalpies in order to calculate the efficiency of a turbine. So now let's have a look at the isentropic efficiency of a turbine. It says that steam enters an adiabatic turbine steadily at 3 megapascal 400 degrees centigrade. This is state 1, and leaves at 40 kilopascal 100 degrees centigrade. This is your actual state 2. I'll represent it as 2A. If the power output of turbine is 2 megawatt, you have to determine the isentropic efficiency of turbine. So the state 2S would be represented by two properties. One is the pressure P2, which is 550 kilopascal, and S2, which is equivalent to the entropy at state 1. So these two would help me find out the enthalpy H2S if I have to calculate the efficiency. This is the process: actual state 1, actual state 2, and I'll write it as 2A, and the actual state 2S I have written as 50 kilopascal, and S2 is equivalent to S1. So for the initial state, state 1, 3 megapascal, 400 degrees centigrade, you have found out the enthalpy as you need it in the formula for isentropic efficiency of turbine, and enthalpy so that you could find out the isentropic enthalpy, which is H2S. For state 2, which is the actual state represented by 2A and 2A, these are the pressure and temperatures, and you can directly find out the enthalpy value H2A from the table. For H2S, the 2S state, the isentropic state, pressure is given to you as 50 kilopascal. S2S, you will find out, you will take it from the inlet condition. These two would help you find out the entropy at second state. So if you see, the entropy at S2S is 6.9235. If I compare it with SF and SG at 60 kilopascal, I would say that this lie in between these two conditions. So actually I am in the mixed region for the isentropic state. So this is my actual process. The isentropic state, basically it comes into the mixed region. So if I have to find out H2S, this region, I need to have the value of HF and HG and the value of quality. For quality, I'll use this value, S2S value, this value. So you already know I'll use S2S, SF and SFG to find out the quality value. And once I have the quality value, I'll plug in the quality value to find out the enthalpy at isentropic state. HF, HFG and the quality value would give me the H2S value at the isentropic state. You just have to plug in the enthalpies, the three enthalpies that you have got, and this would give you the efficiency of your system to be 66.7%. Similar is the case for compressors. The only thing is just the diagram is varying now. Now you are moving from low pressure to high pressure, P1 to P2. The actual process again would be in this way, such that your entropy is increasing. Your essentially the entropy is increasing. The isentropic process or the ideal process is the process in which your entropy is constant. In compressor, since you have to provide work, the isentropic work would be less as compared to the actual work. This is actual. In that case, the isentropic efficiency would be actual compressor work, which is more, with reference to the isentropic compressor work, which is less. So this would exactly be the opposite. The H2S minus H1 is the isentropic work, and H2A minus H1 is the compressor work. We have placed the difference such that we have positive quantities on both ends. So refrigerant R134A, you have this refrigerant enters in an adiabatic compressor as saturated vapor 100 kilopascals. So the inlet condition is X equals to 1, pressure equals to 100 kilopascal at a rate of 0.7 meter cube per minute and at 1 megapascal pressure. So at the outlet, the pressure P2 is known to you. If the isentropic efficiency is 87%, you have to determine the temperature of the refrigerant at the exit. So you know the inlet condition. For the outlet condition, the isentropic properties, two individual properties, P2 is known as 1 megapascal, and S2S, the isentropic efficiency, is essentially equal to S1. So you have the properties, two properties for both the inlet condition and the isentropic condition. The only thing unknown is the actual output condition. So let's first try to see what we can do. For 100 kilopascal saturated vapor, H1 is equivalent to Hg at 100 kilopascal. You have found it out. S1 is Sg at 100 kilopascal. You have found it out. So for the inlet conditions, you have found out the entropy and enthalpy value. For the isentropic condition, you know 1 megapascal pressure, you know that the isentropic efficiency is equivalent to the inlet enthalpy. You'll use these two properties to find out the isentropic efficiency enthalpy, which is H2S. For the actual enthalpy HA, you can now use the formula for the efficiency. Efficiency is known to you as 0.87. H2S is known to you, H1 is known to you, H1 is known to you. The only thing left unknown is H2A, the actual enthalpy. You can find it out from this relationship by just plugging in the values and now using the actual enthalpy and the pressure P2. P2A is 1 megapascal as it has been described, and H2A you have found out. Using these two individual intensive properties, you can find out the exit temperature from the table. All right. Now moving on to the entropy balance. This is the last portion that we'll be covering for chapter 7. Entropy balance, entropy could flow into the system in the form of mass or heat, and similarly could flow out in the form of mass and heat. Other than these two terms, there is entropy generation that is taking place within the system that is contributing towards the change in entropy of a system. This entropy generation could be positive for an irreversible process or equivalent to 0 for a reversible process. So the entropy balance equation is total entropy entering or leaving the system plus this entropy generated. This is an additional term as compared to the energy balance equation, and this would contribute to the change in entropy, total entropy of a system. So S in minus S out plus S generation, this is an additional term, would result in the change in entropy of a system. And if you have to express this in the rate form, everything would be in the rate form. S dot in, S dot out, S dot generation would contribute towards change in entropy of a system per unit time. You've already seen this. You can also specify in terms of mass per unit mass. Small S in, S out, S gen would contribute towards change in energy of change in entropy of a system per unit mass. Mechanisms of entropy transfer, the very basic mechanism known to you is the heat transfer mechanism. So if there is a heat flowing into the system or outer system at a constant temperature, it will contribute towards entropy due to heat. If there are multiple additions of heat coming in at multiple temperatures, you'll have to sum them up together to contribute the entropy towards the system. And entropy transfer by work is essentially 0. There is no entropy due to work, and entropy transfer due to mass is basically the mass flow rate multiplied by the entropy of that mass at that condition. This you can find out from the property tables. So the entropy due to mass is essentially the mass which is entering the system multiplied by the entropy of mass at that particular condition, pressure or temperature. So when you have a closed system, the entropy generation for a closed system is essentially expressed by entropy coming in or going out in terms of heat plus entropy generation is equivalent to change in entropy of a system, which is the entropy change as the system moves from state 1 to state 2. For a closed system, you have ignored the entropy contribution due to mass. So mass is not there. This has been ignored. Entropy generation for control volumes, again, entropy due to heat, whether it is flowing in or flowing out. The entropy coming in the form of mass through the inlet, having an entropy at the inlet as S1. The entropy at the exit, which is leaving the system, multiplied by the mass which is leaving the system, plus entropy generation is equivalent to change in entropy of the control volume as the control volume moves from state 1 to state 2. Entropy generation for a steady flow system. Now you need to know that you have a steady flow system, so the rate change in energy and change in entropy of a system per unit time would be 0, and the entropy generation, entire rate of entropy generation, would be equivalent to the rates at which masses are coming into a system with corresponding enthalpies and the rate at which heat is entering and leaving the system at their particular specific temperatures. When you have a a steady flow single stream, this summation sign would cancel out. You will essentially have same mass flow rate, one exit, one inlet, and the contribution of heat could be multiple. When you have a single stream adiabatic system, this term would essentially cancel out, and you'll have entropy generation entirely due to the mass which is exiting the system and the mass which is entering the system, contribution due to that. So let us have a look at this example which says that refrigerant R134A is expanded adiabatically from 700 kilopascal 30 degrees centigrade, the first condition, to a saturated vapor 60 kilopascal condition. This is the second state. Determine the entropy generation for this process in kilojoules kg per Kelvin. Assume the process to be steady state. So when you have a steady state process, S dot gen is essentially equal to the mass flow rate multiplied by the entropy that is exiting the system and entropy that is entering the system. Since this is mass flow rate is constant, you can divide S dot gen with mass flow rate. You can bring it over here and this would become small s gen, that is entropy generated in kilojoules kg per Kelvin. And this would essentially be equal to S2 minus S1, the entropy of the fluid which is exiting, and the entropy of the fluid which is exiting. So at these S2, you have both the conditions. For inlet, your conditions are known. For exit, your conditions are known. So you can simply find out the entropy due to the mass which is entering at this condition, S1, and the entropy of the mass which is leaving the system at this condition, S2. The difference of the two would essentially give you the entropy generation as a result of this process. And if you see, the positive value indicates that it's an irreversible process. Are there any questions regarding this, what we have covered?